In this video, we're going to go over the equilibrium constant worksheet. So the equilibrium constant is a ratio that expresses the relationship between products and reactants at equilibrium. So the value of this ratio will tell us, is my reaction mixture at equilibrium mostly products, is it mostly reactants, or is it somewhere in between? So there's two types of equations that we'll need to write equilibrium constant expressions for. Those are homogeneous equations where all of the states of matter are the same, and heterogeneous equations where the states of matter differ. So for question one, we just want to classify these reactions as homogeneous or heterogeneous. So looking at A, notice the states of matter of all of the reactants and the products. They're all gases. So since they're all the same, this is going to be a homogeneous equation. In B, we have some gases and some solids, which makes it heterogeneous. C, we have all gases. In D, we have gases and solids. And in E, we have aqueous solutions and solids. So that's also going to be heterogeneous. So now that we're able to identify if a reaction is homogeneous or heterogeneous, now we need to look at how do I write that equilibrium constant expression. So K is the universal equilibrium constant for reactions. There's lots of different flavors of K. There's Ka for acids, or Ksp if you're dissolving something. There's Kp if you're dealing with pressures. But all of these are the same concept. They're all a ratio of the amount of product to the amount of reactant in that reaction mixture. So in order to write an equilibrium constant expression, first the products go on top and the reactants go on bottom. The square brackets indicate concentrations in molarity, moles per liter. And any coefficients from the balanced reaction are going to become exponents. So looking at our example here, C and D are products, so I have those on top in my equilibrium expression. A and B are reactants, so they go on bottom. And then the coefficients, for example, we have 2b, that becomes a square, and on 3c, that becomes a cube. So for these homogeneous reactions, we want to write the KEQ expression. So first, we put our products on top, reactants on bottom. And then any of those coefficients are going to become exponents. So for example, in equation B, we have 4NO2. So that 4 is going to become an exponent on the NO2 term in my K expression. So what about heterogeneous reactions? How do we write equilibrium constant expressions for a heterogeneous reaction? So the important difference is that when you write an equilibrium expression for a heterogeneous reaction, you do not include pure solids or pure liquids. So in this example here, notice that A is a solid and B is a liquid. Therefore, they're not appearing in that K expression. And this is because the amount of moles in a solid versus a liquid is going to be much higher than the amount of moles in an aqueous solution or a gas. And that's because solids and liquids are condensed states of matter. So what this means is that the concentration or the amount of a solid or a liquid is going to be much, much greater than the other concentrations. So effectively, their concentration just stays constant throughout the reaction. So we just exclude those terms because they're not going to affect the value of K. So for each of the following heterogeneous reactions, we want to write the KEQ expression. So for A, again, products on top, reactants on bottom, but notice that we excluded the carbon because it is a solid. In the second equation, I have MgOH2, magnesium hydroxide, as a solid. So we're just going to not include that in our equation. And in C, I'm going to exclude the solid copper and the solid silver and just include our aqueous solutions in my K expression. So far, we've been able to identify if a reaction is homogeneous or heterogeneous and write our K expression. So what does it mean if we have a certain value for K? So if K is very large, remember that this is a ratio of products to reactants. So if K is large, it must mean that that ratio is top heavy, or we have more products than we have reactants. So we would say that the reaction goes to completion if we have a very large KEQ value. So that means that the reaction mixture is going to be pretty much all products. If we have a small KEQ, then that means that that ratio is bottom heavy and we have more reactants than products. So we would say if we have a very small KEQ that the reaction doesn't occur. If the reaction mixture is just basically all reactants and very few products, the reaction doesn't occur. So we have two reactions here, reaction A and reaction B. And we want to kind of examine these and answer a few questions about them. So first we want to write the equilibrium constant expression, and then we're going to plug in some values into that expression to get a value for K. So for reaction A, we have oxygen O2, and that's going to be cubed, and on bottom we have ozone, which is going to be squared. So I'm just going to plug in those given values there, and this is the value that I get from my K expression. So this K is very, very small. It's 3.5 times 10 to the negative 89. So that means you have a decimal point, 88 zeros, and then a 3 and a 5. So this is a very small K value. So because this value is small, the mixture is going to be mostly reactants. Now in reaction B, we have a different equation. So we're going to go ahead and write our K expression and plug in values. And we get 9.99 times 10 to the 24. So that's a huge number, right? So that's like a 999, and then there's 22 zeros that come after that. So a big number. So since K is so large, the reaction mixture is going to be mostly products. So what does this look like? What should the reaction mixture look like? Well, for the oxygen and ozone reaction, we had a very small K value, which means that my mixture should be mostly reactants. So I have one O2 in there, but my mixture here is going to be mostly reactants. Whereas for reaction B, it's going to be mostly products because I had a very large value for K for reaction B. So in number 5, we have the ionization of acetic acid to form acetic acid solution. So if you put acetic acid in water, it's going to break apart into H plus and C2H3O2 into acetate. So we can start by writing our K expression here. Notice that I include charges. These are aqueous, so I need charges on those guys. Now for B, the picture shows the reaction mixture at equilibrium. Do we expect a big K or a small K? So look at this picture, and what do we have more of? Do we have more reactants or do we have more products? So we have a lot more reactants. So we expect a small K value because that mixture is mostly reactants, very few products. So how would that picture change if K had a large value? So then my mixture is going to need to be mostly products. So a large K value means the mixture is mostly products here. So I only have one reactant and everything else has broken apart to give me products. So in question 6, we have the reaction between phosphorus 3 chloride gas and chlorine gas to produce phosphorus 5 chloride gas. So let's start by writing our chemical reaction. So phosphorus 3 chloride. Phosphorus can have more than one charge, which is why we have these Roman numerals here. So in this case, the charge on phosphorus is +3. Now chloride is -1, so I'm going to need 3 of those for every one phosphorus. That's going to react with chlorine gas. Be careful, chlorine is one of those diatomic elements. So instead of just Cl, it's going to be Cl2. And I need a double arrow here because we're dealing with an equilibrium. And then we have phosphorus 5 chloride. So that's going to be phosphorus with a +5 charge, which means that I need 5 chlorides that are -1 to make this neutral. So now that I've written and balanced the chemical equation here, we have the following quantities present, and we want to calculate the value of the equilibrium constant. So first, let me just write my K expression. So products over reactants, all of my coefficients are 1, so everything is raised to the first power or just itself. Now, those square brackets represent concentration. So I need to get the concentration of all of these components based on what I'm given in the problem. So let's start with PCl3. So molarity in chemistry is how we measure concentration, and that's going to be moles per liter. So I already know the moles of PCl3, and we're given that the volume is 3 liters. So I just need to solve there for my concentration. Now for the chlorine gas, we are not given moles, we're given 52.3 grams. So what we're going to want to do here is take that 52.3 grams of chlorine, and we want to get molarity. So I need to get my grams into moles by dividing by my molar mass, and then I need to divide by the 3 liters. So that gives me my concentration there. And for the phosphorus 5 chloride, we're given moles, so we just got to do moles over liters. Now that we have all these concentrations, I can go back into that K expression and plug in numbers for all of these values and solve and get my answer here. So the value of K here is 6.4. That means that we have a little bit more products than reactants, but it's pretty much the same amount of products and reactants. If K was much, much larger, then it would be all products. If it was much smaller, then it would be all reactants.